So in our previous video, we covered a complex process by which we can turn salt into powerful oxidizers. And so we ran this project for the course of like 3 days or so, because a rainstorm stopped us. Last Monday, I took a look at the inside of the machine, and apparently the electrode had broken overnight. Like we discussed previously, the graphite reacts with the material we are producing and slowly gets destroyed. At least the binder gets destroyed inside the graphite. So it basically just becomes a dust. So I replaced the electrode for its 3rd day in operation. And then that night I had to do a distillation and separate out what we produced and the liquid. I filtered out any metal materials or anything that just was debris or stuff that was in there. I used this new material as a filter. Usually I use absolute garbage, but I've decided to use this for this part. I do not really have time to talk about the reaction in detail in this episode, but I talked about it in detail in a video previously. So this is the first time we're actually able to do a distillation because, usually, well, the last time we did this, it exploded and I was no longer allowed to do a distillation, but we're doing it here. Thank goodness this one didn't explode, but it did just space stuff everywhere until the end when I discovered a method to prevent it from doing so called stirring. You just stir it and the bubbles don't explodicate everywhere and just become crystallized on different materials. So I started this procedure at 6:38 p.m. on Monday, which is before I had school, and I ended it about an hour past when I was, well, 2 hours past when I was scheduled to sleep. At 10 p.m. It took 4 hours almost. And the thing is, those 4 hours were not well spent because guess what we did not get from this? We did not get any chlorate. In fact, I'm pretty sure we got a whole bunch of other stuff too that we did not want. Regardless, at the time, I was not really sure, and I did not really know, and I was just like, oh yeah, this probably is stuff we're looking for, and it kind of smells like the stuff we're looking for, probably. I don't really know what sodium chlorate smells like, but I assume it would smell like bleach. So I've been really getting into actual sodium and those first row chemical, like, they're actually interesting. Like, usually, everybody gets interested in those because they react with water, right? You know, because they're super reactive. Well, funny thing is, these things actually are able to store oxygen or hydrogen in different ways. For example, there is sodium hydride or lithium hydride or the various hydrides of those first row, and they can store a lot of hydrogen for, like, what, a gram of the stuff? For example, I was reading a paper about lithium hydride, and it said that lithium hydride can store... a gram of it can store 2.5 liters of hydrogen. And with sodium chlorate, here's the interesting thing. You can actually cause it to decompose and release oxygen just by heating it to 300 Celsius. But on its own, because of the chlorate ion, it's a very powerful oxidizer, just like on its own. It's got, you know, chlorine and 4 oxygen. Or, not 4 oxygen, 3 oxygen. That's 4 oxygen would be something else. But I feel these properties actually lend it pretty useful to rockets. So I was kind of interested and just decided to go ahead and build one for some reason. This was a complete waste of time because what I had was table salt. Now the thing is that the reaction we're going to use for this, or we were going to use for this, essentially would use sugar as the fuel and the chlorate as a way of, well, producing oxygen for the combustion of the sugar, as it actually takes extra oxygen for the sugar to combust. Like, yes, sugar can burn on its own in the air, but if you add oxygen to it while it's burning, it's going to burn so much better. In fact, a reaction I once saw demonstrated to me used potassium chlorate and decomposed it into calcium chloride, which releases the oxygen, of course, because these chlorates of these first row, they decompose. Not all of them, and it's you'd have to read about them to find out. But in the case of sodium chlorate, we can decompose it. So that was my idea. But there was a few problems against me. First of all, I had sodium chloride. Second of all, this was soaked in water still somehow, even though I had thought I dampened it, or, well, not dampened it, I mean, dried it, I should say. So when it finally came to launch, and I thought this was gonna go exorbitantly well, the end result was just burnt sugar. I mean, it was, we had way too much sugar in the ratio as well. Maybe. Potentially, actually, yeah, probably. Most likely, definitely. Honestly, I don't know what the ratio should be. I don't know what the ratio should be. I can't do math. But you'll see later I try again, because I still did not know what I had. Because it did smell correct, and it looks correct, and it seemed correct. I probably would taste correct, but I didn't want to taste it. Regardless, I attempted to get it to go, and it actually, the sugar was melting out and burned, and it was interesting because it just kept coming out and fueling the fire, and it looked pretty cool. But did not go anywhere. And I'm kind of thankful for that, because it could have ended badly. But we'll try again in the future if we ever have something stupid to do. like if we have chlorine trifluoride or something. If I ever get my hands on some of that, we'll shove it in there and use that as an oxidizer, and then we'll use one of the metal not metal. We'll use sodium aluminum tetrahydride as the fuel because that is a very good combination. That's combining a strong reducing agent with a strong oxidizing agent, which is obviously the chlorine trifluoride is the oxidizing agent, and the reducing agent would be the other thing. And like I said, I'm bad at math, but I did the calculation for this, like using the bond energies and stuff, and it seems like it gives like it gives a lot of energy. It gives way too much energy. Like, they're both very not stable at all. They don't want to exist. And then when you combine two things that don't want to exist, and they both are opposites of each other, you end up with something incredible. Which you basically end up with a lot of energy from that, and that's why it's interesting, because... And also, the other thing that makes it a lot of energy is because the stuff on the other side would probably be high energy stuff, high stability stuff like sodium, like salt. Anyway, the leftovers of what we had produced, I distilled them today, in fact, just so I could finally end this urge to do this reaction where we have a lot of oxygen produced and end up like with like a massive amount of energy. I'm getting better at these distillations. Maybe I'll get like an actual distillation column so we can recover some of that water. I don't know. Because I do have a project on plan that needs me to get a gas mask because it's going to require melting plastic, and I don't really want to get plastic inside my lungs. I don't feel like doing that at all. But then again, I think I could probably do it without a gas mask, honestly. As long as the plastic doesn't burn, it should be fine. The thing is, you don't want the plastic to burn. Now, if you're doing with polyvinyl chloride, I advise caution because, of course, VCM monomer is not very great. So, you do that with caution. With polyethylene, or with, like, something else, it's probably fine. Like, what, if ethylene comes out of the polyethylene, it's just gonna smell bad, right? I actually did switch out the container to a smaller one, so that way I could distill it better. I'm using these flasks because they keep the bubbles in it. You know, the ones that go like, poof, and they just shoot out everywhere? That's not fun. It's also at this point in the video where I actually start using that new technique where we use a beaker instead and just stir it. I don't want to do that constantly, so I would like to use the flasks, and then once it gets down to the point where it starts going poof, 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 I just want to go stir it in the beaker instead. Because that's just optimal, because it takes like 6 years to do a distillation. Equipment I need to put down on my list of equipment to get is hot plate, gas mask, variety of other stuff. There's a lot of stuff. Distillation columns. There's a variety of different columns that you can attach to these things that they do various things. Okay, they're important. Those pieces, I don't have those. I'd be very happy to have some of them pieces that you can just connect, and it goes and does the stuff with them. And then there's the bench clamps that allow you to like mess with the stuff. Probably sounds like I have no clue what any of this equipment is. I don't know the exact names for any of it, but like I know what it does. Okay, so after the second distillation, here was the correct mixture of ingredients, I think, and yeah, I could not get it to ignite, even like when I added stuff to it to make it ignite for you all. I didn't want to leave you all on the note where it doesn't ignite, but and actually with the rocket previously, we did put a little bit of ethanol into that thing to try to make it ignite, but it did not ignite. And with this, it also doesn't ignite. Now, the reason this does not ignite is because salt, it just doesn't burn. Salt does not burn. Salt is not flammable. It does not burn. Sugar is flammable. It does burn. Pouring salt on a fire probably would not extinguish it. But you can use salt in alloying certain, like gold and silver, I think I've read about. Actually, in the process of doing gold refining, historically, I think they use salt. And the way that works is basically you end up with silver chloride and then just gold, which is nice. But I haven't finished reading that. I have to finish reading about that. So the thing is, I don't know when I'm gonna get to that because I'm busy reading about my hydrides, you know. Anyway, I hope you all have enjoyed this this failure of an experiment. But we will be revisiting this in the future and reattempting this. I have another issue with this. Again, we used iodized salt, which is a mistake because sodium iodide it contaminates the experiment quite a lot. So we could have formed sodium iodate, which would react with the hypochlorite formed in the initial steps to produce something else called sodium periodate. And now this stuff does, I don't know anything about it. I have not read about it at all. I'm literally just looking at the Wikipedia right now for about this because I was interested in iodized salt. What is the iodine gonna do in my reaction? I haven't read anything about iodine. I probably should go read about iodine. I think that's what I should go do now. Maybe next time we should do an iodine video. What can I do with iodine? And where can I get it? Oh, we're gonna need to go find a river biome. Or actually, we could go to the ocean and get seaweed. And then burn the seaweed for the solid iodine, which also turns your hands brown. Iodine does, I think. There's also bromine, which is something else in the family of chlorine, and I don't know why I like the things on the far edges of the table, but yeah, I kind of seem to like the things on the far edges of the periodic table. The things that are very reactive, or the things that are very powerful oxidizers. What? I don't know why I like these things, I just do. But anyway, with the iodine, you just burn seaweed, right? With bromine, you have to extract it from a river, which is, or an ocean. You can also get it from seaweed, but that's just a different method. I don't know how to do that. I've been reading about bromine a little bit, but I probably would need to read more about it. I just know you get it from a river or the sea. That's all I know about. Anyway, I guess I'll get started on that next thing. I guess I don't know. All right, I need to go start reading about whatever I said I was gonna read about.